Hello ladies, sorry I can't join you for class today, but instead I figured I would create a recorded lesson for you. That's a little reminder of synthetic division first we'll do, and then afterwards I'm going to show you the rational zeros theorem and how we're going to use that next week to start factoring some complicated polynomials. So I figured to start out, I have the homework listed here, and again, this is listed on Blackboard as well. So after you're done with this lesson, feel free to go ahead and get started on this homework assignment and get it done with so you don't have to worry about it for the weekend. I also wanted to note, our quiz will not be today since I didn't see you on Thursday for Gretna Day. Hope you enjoyed it. But I figured we'll move the quiz back to Tuesday then, the next day I see you. So again, here's your list of quiz topics again. Feel free to pause the video if you need to look at these a little bit more. It's the same list from Tuesday. Also, the list is posted on Blackboard as well. Under this week's topics is also on the right. So I did post your homework. Feel free at any point, I'll kind of scroll through and talk about certain ones in particular occasionally. But feel free to pause if you have any questions and want to check your answers. I have your polynomial form and your fraction form for your final answers for each of these. For number 4, typically you don't end up with fractions like this. So don't worry if you had a little bit of a difficult time with this one for your final answer. You do end up with a fraction as your remainder. But again, yeah, you don't see this very, very often though. For number 6, this one does have a remainder of 0, which does mean that this particular divisor is a factor of this function. And using the remainder theorem, remember we solve each divisor as a 0, set it equal to 0, solve for x, and then from there we plug that x value into the original function you were given and evaluate it. And whatever answer you end up with ends up being your remainder. Okay. So if you have any questions, write it down for me. When we return on Tuesday, I can answer any of these in more detail if you'd like to go over any of them. Right? But let's jump into synthetic division today. So we talked about long polynomial division earlier this week. So if you remember, synthetic division is another way to do your polynomial division, except for it's only used for one specific type of divisor. And for your divisor in this case, it has to be x plus or minus a value. So we used k in the past. So it has to be in this particular type of form in order to use synthetic division. So if you remember synthetic division, I have a copy of what this looks like for this particular example, and I'll go over where everything comes from. But basically, the box here, the number that's in this box, we get as that is the 0 of our divisor. So we take our original divisor, just like you did for the factor theorem, for the remainder theorem, and we solve this for x, and that number is what goes inside of the box there. The numbers that are to the right of that box, those are the coefficients of our dividend. So notice the 2x to the third power, we only use the coefficient of 2 out front. The negative 3, the negative 5, and the negative 12. So one thing I do want to point out, if, let's say, for example, this particular problem was missing the x term, make sure in synthetic division you add a 0 in place.
Hi everyone, congratulations.
Sorry for the interruption, girls. I'm trying to record during lunch during Gretna Day because my plans are all changed unknowingly. Okay, so I was saying, based off of if we were missing this minus 5x term, make sure you put a 0 in your synthetic division. We do need to have place settings for every single one of your terms here. If we miss something, it's going to throw off your entire answer. But just getting into where these numbers in the bottom are actually coming from, we always start with the first number and we bring it straight down right away. So then from here, we take that number, multiply it by your divisor, and that then becomes the number underneath the next term in our synthetic division. So that's where the 6 comes from. Then we add these two together. That's what makes synthetic division a little bit easier than long polynomial division, the plus sign here. Because remember, in long polynomial division, we have a subtraction sign every time you go through and find a new term you're multiplying by. And sometimes it can be a little confusing when you're subtracting negatives and all that. But with synthetic division, it's just straightforward adding. So when I add -3 plus 6, I end up with a +3. Now I multiply that by the 0 divisor again. That's where this 9 comes from. Add these two terms together, 4. Multiply that by the 3 once again. That's where that +12 comes from. And in this case here, I end up with a 0 when I add it with the -12 already there. So if you remember with synthetic division, the last term in your answer that you're left with, that is our remainder. So that's going to be what your R value is equal to. The rest of this, if you remember, is the polynomial that you have left when you divide out the x minus 3. So what I always do in this case, I always start with where the remainder is and work my way to the left direction. So I notice to the left of the 0 is a 4, so that 4 is going to be our constant term. The 3, the next one, is going to be our x term, and the 2 is going to be our x squared term. So if I went through and wrote this in your polynomial form, let's say we had 2x to the third power, our divisor, 3x squared minus 5x minus 12 equals our divisor that we had, which was x minus 3, times the polynomial, our quotient in this particular case. So 2x squared, it's a positive 3x plus a positive 4. And since we have a remainder of 0, I don't even have to add that in here. So we're going to use synthetic division a lot in the future here to help us to factor, especially things that are like cubics, or to the 4th powers, or even up to the 5th powers. We're going to do a lot of these types of problems. Right? So what I'd like you to do now, pause the video, and I'd like you to try using synthetic division for this particular problem. When you are all finished, go ahead and unpause and we can check your answer. So I'll get started on this one. Reminder, inside your box for synthetic division is always the 0 of our divisor. So if you set it equal to 0, solve, end up with a -1. Looking at my dividend, it looks like we have every single term in order in this case. So I'm just going to use the coefficients out front. -5, +3, and then -2. Don't forget about those negatives as well. Let's see. So I'm going to put my plus sign. And I think I forgot to mention, they want our final answer in fraction form. Right, so let's see, I'm going to bring down my 1. 1 times -1 gives me -1. Add with the -5 gives me -6. -6 times -1 is a 6. Add it with the 3 is a 9. 9 times -1 gives me -9. And we end up with a remainder of -11. So I'm going to box off the remainder. And working in the left direction, that means 9 is our constant value, -6 is our x value, and +1 is the x squared term. So let's see, if I write this out, we have our dividend, which is x to the third minus 5x squared plus 3x minus 2 equals our divisor, x plus 1, times our quotient. And I'm doing polynomial form first just because it's easier to go from polynomial form to your fraction form. We have x squared minus 6x reciprocal, make it minus 11. And remember, we said it's super easy to go from your polynomial form to the fraction form just by dividing everything by our remainder divisor. So we are left with, for our final answer, our dividend divided by our divisor equals, notice divisors eliminate each other, minus 6x plus 9, minus, and we'll keep this as 11 over x plus 1. Okay. And this is our final answer in fraction form. Okay. So hopefully synthetic division's coming back to you, because we are going to be using this shortly here, but I wanted to show you a new theorem that we're going to use a lot when we're going to be factoring a lot of these polynomials. So first thing we're going to start out with is called a rational zeros theorem. Basically, what we're going to be looking at for polynomials is all the real zeros. Real zeros meaning all the zeros that actually cross on the x-axis. So they're actual values for your x-intercepts. We're not dealing with imaginary zeros yet. We'll get to that next week, so hold tight. But as far as real numbers go, there's two different types of real numbers. We have rational, so we have rational zeros, which rational numbers, and if I cover up the last three letters of the word rational, you are left with the word ratio, which means fraction. Technically, if you can write any zero as a fraction, it's considered rational. Irrational, of course, is the complete opposite. If we can't write it as a fraction, it's irrational. So kind of the rule of thumb with these, any zeros that when you go through and solve, you end up with a fraction or even a whole number, because remember, if your answer is like x equals 5, we can always write that as a fraction of 5 over 1. But usually the irrational zeros we're going to use the most are going to be square root answers. So values that are square roots that we cannot easily write as fractions. So the rational zeros theorem, technically what it does is it allows us to look at a polynomial equation in standard form. So with your largest degree first, your constant last. And it allows us to come up with a list of all the possible rational zeros you could have for your polynomial. So this is giving us a possible list. It doesn't mean all of the values that we come up with are actually going to be zeros. It just means that of all the rational numbers in the entire world, we're looking at a small number of them that could possibly be zeros. And we'll check out how we'll be able to actually calculate which ones are the zeros with your calculator. Okay. But first, looking at your actual standard form, we are going to calculate two values, a p-value and a q-value. And then to figure out all your possible rational zeros, we're going to calculate all possible p's divided by q's. So, sounds a little confusing to start, but let me give you kind of like a little example. Let's say in a polynomial, let me just make up one. Let's say we have 2x plus 7x minus, let me do 4. Do 4. Yes. All right. So the p-value that we're going to come up with here, p is always going to be an integer factor of our constant coefficient. So we're looking for what integer values could divide into our constant coefficient. So looking at this example, our constant coefficient, of course, is the -4. So we want to try and figure out all possible factors of -4. What are numbers that divide easily into -4? So what we have, and we're going to include both positive and negative integers in this. Positive and -1 is a number that goes into -4. Positive and -1 is going to exist for every single one of these. Positive and negative 2 is also a number. That's an integer factor of 4. And positive and negative 4 itself as well. Now your Q value is going to be an integer factor for your leading coefficients. So we're going to look at the positive 2 out front. And we're going to come up with our Q values. So Q in this case will be positive or negative 1 and positive and negative 2. So to find all the possible rational roots, we are going to divide every single possible combination of P divided by Q for all the ones that we have here, all the values. So we're going to look at P divided by Q. So let's see, I'm going to start out with the very first P value, the very first Q value. So I have positive and negative 1 over positive and negative 1. So that's a possible rational zero, or two rational zeros we could possibly have for this problem. I'm going to do then positive and negative 2 over positive and negative 1. And I'm going to do positive and negative 4 over 1 as well. So just doing combinations of all the P's divided by that one Q first. Now I'm going to go through and do the same thing, but with the second Q value. So I'll have a positive and negative 1/2. Well, because I already have a positive and negative, yes. Right. And I'm going to have positive and negative 2 over positive and negative 2, which we already technically have with the first term, which just simplifies to 1. And we have positive and negative 4 over positive and negative 2, which also simplifies to 1 we already have listed. So thinking about all the rational numbers in the entire universe, you just got your possibilities as zeros down to 8 possibilities. So 2 for 1, positive and negative 1, positive and negative 2, positive and negative 4, positive and negative 1/2. So again, this is just a list to help get us down to a smaller number of possible rational zeros. So let's look at an actual example of this and how we're going to use it. Right, so starting out, in this particular example, everything's written already in standard form. So we can go through and find our P and our Q. So your P value in this case, again, remember, always the last constant value, and it's a factor of that, which in this case, we're very limited. It's just positive and negative 1 only. Whereas for our Q value, remember that's always the leading coefficient of our problem. So we're also limited by this because it's just a positive and negative 1. So if we're looking for all our possibilities, I'll put possible rational zeros. So we're going to do our P divided by Q, which technically that leaves us with just 2 possibilities here. Just a positive one or a negative one. So what I'd like you to do at this point, let's pause the video, and I'd like you to plug this function into your graphing calculator in the y equals form, because we want to graph this particular function. So once you have the graph and you are able to look at it, I'd like you to look for, on the graph, does it look like your graph crosses the x-axis at either of these possible rational zeros? Does it look like it intersects it at positive 1 or at negative 1? And I graphed mine here too and put a screenshot of this. Notice this does not look like it intersects at positive 1 or negative 1. So remember, these values that we have here are a list of all the possible rational zeros. So since none of these actually work, that means for this particular problem, the 3 zeros that we have are all going to be irrational instead. And we'll talk about in a little bit later on this unit how to actually find those at this point. But for right now, I just want you to deal with rational zeros only. All right. So let's look at this next example. So what I'd like you to do is go ahead and pause this video, try this particular example, try to find all your possible rational zeros, and go ahead then and use your graphing calculator to come up with which from your list of P's and Q's actually does work. Right? So pause it. I'm going to get started on it. When you're done, go ahead and unpause. All right, so I'm going to start out with my P's and Q's here. So with P, remember it's always the constant value, a factor of it. So positive and negative 1, positive and negative 2. And our Q's are going to come from our leading coefficients, positive and negative 1, positive and negative 3. So as far as our possible zeros in this case, we could have positive and negative 1. We could have positive and negative 2. We could have positive and negative 1/3. And we can have positive or negative 2/3. So, graphing calculator time. Plug this original function into your graphing calculator. Let's see what this looks like. Ooh, so looking at this particular function, I'm going to put ones that we think might actually work here. I'm going to list them. So it looks like we're thinking maybe positive 1 works. We're thinking maybe a negative 2 works. And we're also thinking, could be negative 1/3 or negative 2/3. I'm going to put both possibilities just because it's kind of hard to tell just from looking at this graph. But both of these are possibilities. So what we could do at this point is we could use your remainder theorem that we looked at earlier this week. So we could actually take each of these zeros, so like x equals 1, plug it back into the original equation for every x value, and see if we get a remainder of 0. If we get a remainder of 0, we know then that that particular x value is in fact a 0. Or we could even go through and use our synthetic division here. So let's see if x is equal to positive 1, and I'll show you how we're going to use this for factoring purposes. And let me write out my original is 3, 4, negative 5, negative 2. So I just picked one to start, just because that was the first one I noticed. You could technically pick any of them here. So I'm going to bring down my 3, multiply 3. We end up with a 1. And, I'm sorry, 7. I'm adding, not subtracting. 7, with a 2, 2. Oh, notice I do end up with a remainder of 0. So that does work in this case. So what I want to show you is since I have the positive 1 is a 0, I know x minus 1 is actually a factor. And this is something this problem didn't ask you to calculate, but I want to show you kind of where we're heading with this. And let's see, we end up with this 2 being the constant, 7 being the x, and 3 being the squared term. Okay. So what we could do next here is, now that we know 1 is definitely a 0, looks like negative 2 is as well. I'm going to use this method again with the synthetic division. And what I'm actually going to use as well is, for my dividend this time around, I'm going to use the quotient from our previous problem. So we use the 3, the 7, and the 2. I will show you why here in a second. So I'll bring down my 3, negative 6, and positive 1, negative 2. Ooh, I have another remainder of 0. So what I want you to see in this case, from this problem, I still have the x minus 1 that I technically factored out already. And now with what I have left here from my divisor, I have an x plus 2. And then from what I have left over is a 3x plus 1 for my quotient, which we actually just used the synthetic division And if you notice, we end up with an x value of positive 1, we end up with an x value of negative 2, and we end up with an x value of negative 1/3. And since our problem, our polynomial has a degree of 3, it ends up working out that we have all 3 zeros here, and they are all rational. So this is super handy when we're trying to figure out the factored forms. So one other thing I just want to point out for you, because sometimes with these types of polynomials, if the bigger the numbers you have here, the more P's and Q's you're going to have, as well as the more possible rational zeros you are going to have. So there is a little cheat to help you get your number of rational zeros down. And this is where we use upper and lower bounds for these real zeros. So basically, let me show you what we're talking about here. With these types of problems, I'm basically going to give you an interval and ask you to show that your lowest bound number is telling us that there are absolutely no zeros below that value. So like let's say here, for example, I give you the interval of 0 to 5. Let's say, so in this case, if I'm looking at first the 0 value, if we're saying that 0 is the lowest possible bound we could have for all your zeros in this polynomial, that means we know that there are absolutely no negative values used as zeros. So we can actually cut all those negative values out from our P divided by Q's. Whereas if we're saying 5 is the highest possible zero value we could have, that means there's going to be no zero value greater than 5, and we could cut all those possibilities out. So as far as the test goes, the test actually uses your synthetic division for this. So in the interval that they give here, I'm going to make this C and this D, kind of like they had in the previous example. So what we're saying is, let me make this C, if we're saying that the smallest value C in this particular case is used as our divisor, our zero for divisor, the last line of your synthetic division is going to tell us if this is a lower or upper bound. Oops. This is a lower bound. I have these two flip-flops. Sorry. This is a lower bound. This is the upper bound. So the last line in your synthetic division, it says if every number in the last line is non-negative, so it's only positive or zero, then we know that that particular value for D is in fact an upper bound. It means we won't have any values greater than it as rational zeros. Whereas if we use the smallest number, try to show it's a lower bound, the last numbers in our problem are going to be alternatingly non-negative and non-positive. So like for example, let's say you get through and you have like 5, 0, 0, -2, 7, -4 as our last line in your synthetic division. So you're only looking at the non-negative and the non-positive. Yes, because they're alternating. So in other words, we're not worried about the zeros here. We're just looking at the actual numbers themselves, which notice 5 is positive, the next actual number is negative, the next number is positive, and then negative. We're not using zeros in these. So let's show you exactly what I mean by this. I know this wording is a little confusing. But let's say for this problem, we want to prove that all the real zeros of this polynomial lie in the interval of -2 to +5. So what we're going to do first is we're going to check the lower bound first. And for the lower bound, we're going to use the -2, the smallest number. And I'm going to put that inside of our synthetic division box where our divisor goes. And I'm going to put everything else from our original divisor of 2, -7, -8, 14, and 8. So in this particular case, I'm going to go through now and do my synthetic division with this number. We have -4, -11, I have a +22, which gives me 14. I have a -28, which gives me a -14. And then I end up with +28, which gives me 36. So looking at my last line here, notice I go positive or negative, positive, negative, positive. Since they are all alternating signs, that means that x equals -2 is a lower bound. So we know if we create our list of possible rational zeros, anything less than -2 will not be considered. We'll do the same thing with the upper bound as well. Let's see, we have a 5 for this one. So I'm going to put 5 in here, and let's do upper bound. All right, so I'm going to use the same numbers from the original, because we're just looking at the original polynomial in this case. And hold on a sec. All right, so we finished off our synthetic division. All right, so notice our last line here is all positive numbers. So since these are all positive numbers, that means we do have our x equals 5 is an upper bound. So basically, that's just telling us that we will not have any rational zeros beyond positive 5. All right. So that is all I have for today. Sorry this video went a little bit longer than I wanted it to, but bring any questions you might have throughout it with you on Tuesday when I see you next, and we'll go over this before we take our quiz. All right. So have a great weekend, girls. Good luck with the homework. Go ahead and get started on that now and get it done. All right. Have a good one, girls. I will see you on Tuesday.